overflow, you have to somehow make a program counter to point within the stack. That's the trick. Because program counter usually points to the instructions that are saved somewhere else, right? So here's an example of stack of activation records. Let's say you have a function g, and then you have a function and then return here. You have a function f. You call g one time, and then the next instruction, let's call it L1, and then you call G again, and then the next instruction is L2, and then it returns. So in this call to G, after G terminates, I want to come back to instruction L1, right? And for this call to G, I want to come back to L2, right? That is important. You need to remember where to come back to, right? It is not always the same place, just like this example. So when this thing runs for the very first call in your stack, you have an activation record for F. And F calls G, and for G you have return address. Let's say it's the very first call, so that return address would be L1, right? When G terminates, we want to go to L1 and execute there. When G terminates, this activation record will be popped off the stack. This one will become active, which is what we want, right? F. And we want to execute starting from L1 on, right? Right? Isn't that the picture that you have in mind as well? You also have save frame pointer. And this is a pointer to the stack, to the activation record that called us, so that when we pop this one, we know where to go to, right? This becomes active. Some systems do it by having the size of this activation record and subtracting it from the stack pointer. If the stack pointer is pointing to that, and you grab the size and subtract it from that, then the stack pointer goes down here, right? Or you can use a pointer and don't store the size. And then there's also a frame pointer that points to the bottom of the stack, which we didn't have this, and this helps us locate everything else in here, because it's a displacement from here, everything that exists in the current activation record, right? So when we pop this thing, frame pointer comes down here, stack pointer goes where the previous frame pointer was, right? So this is the initial thing, and up here would be all the variables and parameters that belong to G, right? Those automatic variables, right? So now to have buffer overflow, let me just see if that thing is there. Yeah. program that overflows a buffer. Okay, so here's that program. So you have a buffer of buffer size. There's an underscore here. So buffer size is 256, right? And you come down here and you say string copy argument value 1 into the buffer, right? So if I run this program like this, a.out, and type something longer than 256 here as argument value 1, right? This is argument value 1, right? It will overwrite it onto that buffer, and it's going to go beyond, past beyond of it. It's going to go past the size of this buffer, 256 and then some. And there you would have your problem. So the problem is this function, string copy, strcpy. And if you don't want to get buffer overflow, you would use this function, strncpy, string n copy. And for the string n copy, you have to specify the maximum number of characters that you copy. Otherwise, it will not compile. Look up string n copy. And this is one of the questions that people ask, potential applicants for security jobs, if you want to get into some company that work on security programs. A typical question is, if you don't want to get buffer overflow, what do you do? And you say, I use string n copy. Okay. So this is the program, okay, that grabs argument value 1 and copies it onto the buffer, and this guy can be more than 256 bytes. Okay, so let's see. Very simple program. So buffer overflow program figure 15.2. And then the other things that you need to do is to write a malicious software. And this would be your malicious software. Name, another program, character, asterisk, command, equal to, remember we did this? So basically, in this program, I want to run a shell command. So exec vp shell and command. So you write this program, right? Very simple program that brings up the shell. So compile, the program, attach new return address. Stack pointer plus 4. So one more word. So you write this program and you compile it. You get a.out, right? Produces a.out. Run a.out. Run buffer overflow program with a.out. So this buffer overflow program is the one that we looked at, right? With the string copy. So prog a.out, like that. You run it like that. So what happens is, if you want to look at this, you have something along these lines. We're running out of time again. I hear them. So new return address. Okay, so this is the code, the bytes for this program here, right? That creates a shell. And then I have added a new return address at the end of the program, right? So when I run this, let's see quickly again. And then we run out. This is what happens in this stack. You're going to get 1, 2, 3, 4, 5, and then a new return address in there. And then this new return address, I set it up so that it would point to the very first instruction of this program. And as soon as this program, popped, we are jumped back to the beginning of it, which is in the stack, and I would start executing this shell program. And if I have root access to begin with, I'm executing this shell program with root access, and I can do anything. Because this new return address should jump me to L1, right? But now I have overwritten it with my buffer overflow to have this address that I have already programmed in my code. If you want, I can show it to you some more in my office, but that's it. See you on Wednesday.
We'll just study up from chapter 14 to 15.
Yeah, just the things that you did.